You spilled coffee this morning, perhaps on your shirt, perhaps on the table. You cursed. You cleaned it up. You moved on. Gone, yes? The coffee soaked into cloth, evaporated into air, became part of the background chaos of your kitchen. Erased. Except physics says no. Physics says the consequences of that spill are still here. Every molecule of that coffee, every bit of heat energy it carried, every photon that bounced off the spreading stain, in principle, all of it still exists, encoded in the present state of the universe. The universe has forgotten nothing. I know how this sounds, like mysticism, like someone who has stared too long at equations in the dark. But by the time I finish, you will understand exactly what I mean. You will see why the past is not a ghost, not a memory, but a place, as real as the chair you sit in, simply located elsewhere in the architecture of space-time. Let us begin simply. Tonight, if the sky is clear, go outside. Look up. Choose any star. Now tell me, what are you seeing? You will say, a star, naturally. And I will tell you, no, you are seeing the past. Light moves at nearly 300,000 kilometers each second, fast enough to circle Earth about 7.5 times in a single second, or almost once in the time it takes you to blink. But the universe is vast. Even light takes years to cross it. Proxima Centauri, our nearest stellar neighbor, is so distant its light requires a little over 4 years to reach you. So when you look at that star tonight, you are not observing it as it is now. You are observing it as it was, a little over 4 years ago. You are receiving mail from years past. Polaris, the North Star, its light began traveling a little over 400 years ago. When those photons left, Shakespeare was alive. The scientific method was being invented, and here they come now, arriving at your retina this very second. Or Deneb, that luminous point in Cygnus. Its distance is debated, but its light has journeyed well over 1,000 years. When it departed, the Roman Empire was a fading memory. The Tang dynasty ruled China. You are catching photons that witnessed the early Middle Ages. The Andromeda galaxy, that faint smudge on a moonless night, its light has traveled 2.5 million years. When that light began, there were no humans. Our ancestors were early Homo, brains far smaller than ours, just learning to shape stone. And yet here comes that light, streaming into your eye right now. The past is not gone. The past is arriving, constantly, from every direction. Every direction you look, you see a different epoch. Your hand, a few nanoseconds ago. The wall, tens of nanoseconds past. The moon, 1.3 seconds. The sun, about 8 minutes. You are swimming in history. Every photon is a courier from another time. Some left milliseconds ago. Some left before your species existed. Suppose the sun vanished, just gone. How long before you would know? About 8 minutes. For 8 full minutes, you would see it hanging there, feel its warmth, have no idea. Then the last photons would arrive and the sun would disappear. The universe does not communicate instantly. Information propagates at light speed, always. This means you are always looking at the past. The present is, in that sense, unseeable. But this is merely the beginning. Now something deeper. Something about the laws themselves. Consider Newton's laws. In an ideal, frictionless world, a ball rolls across a table. Newton tells you precisely how. F equals ma. Elegant, simple. But Newton noticed something curious. His equations do not distinguish between forward and backward in time. Imagine I film a billiard ball rolling, striking a cushion, rebounding. Now I play the film in reverse. What do you see? A billiard ball rolling, striking, rebounding. Could you tell which version was forward? No. Both obey Newton's laws identically. Two balls colliding. Film it, reverse it. Still two balls colliding. A pendulum swinging. Forward, backward. No difference. This is time reversal symmetry. Many of the fundamental laws work equally well in either direction, provided you also reverse velocities. Mathematically, Newton's law involves the second derivative of position with respect to time. A second derivative is unchanged if you replace t with minus t. The sign of time does not appear. Now you will object, but surely I can tell which way time flows. Eggs break but never unbreak. Coffee cools, never heats. Glass shatters but never reassembles. Absolutely correct. But here is the puzzle. The laws governing every atom in that egg are, to an excellent approximation, time symmetric. They work perfectly in both directions. So, why does the egg break but never unbreak? This is one of the most profound questions in physics. We will answer it. But first, deeper still. Quantum mechanics. This is where strangeness intensifies. In quantum theory, we describe systems using a wave function, a mathematical object encoding everything the theory allows you to predict about the system: where outcomes might land, how fast particles move, which way they spin. The equation governing this is the Schrödinger equation, and for an isolated system, this equation is reversible. If you know the quantum state now, you can calculate what it will be in the future, and, in principle, what it was in the past. This is called unitarity. It means the evolution preserves information in the full quantum state. Nothing is created or destroyed. Information is transformed and redistributed. Think of a perfect translator between languages. Every sentence in A corresponds to exactly one in B. Nothing lost. You can always translate back. That is unitarity. Or imagine the universe as an enormous jigsaw puzzle. At every instant, pieces are arranged somehow. Physics tells you how to rearrange them from one moment to the next. For an isolated system, the rule is 1-to-1. Each state maps to exactly one next state and exactly one previous state. What does this mean? If you knew the complete state of that closed system now, you could, in principle, determine exactly what it looked like before. The past is still contained in the current arrangement, though scrambled beyond recognition. Physicists call this information conservation, and we take it extremely seriously. Because if fundamental evolution were not unitary, quantum theory, as we know it, would have to change. Let me tell you how seriously. For decades, we fought about black holes. A black hole's gravity is so strong, nothing escapes, not even light. Things fall in, they do not come out. So we thought black holes were ultimate information shredders. Throw a book in, and it is gone forever. Then Stephen Hawking discovered something remarkable in the 1970s. Black holes slowly radiate energy. They evaporate. A solar mass black hole would take around 10 to the 67th years, but eventually it vanishes. The problem? That radiation looks thermal, like noise. So when the black hole evaporates completely, where does the information about everything that fell in go? All those books, stars, astronauts, where? This troubled us enormously. Hawking argued information was destroyed. Others, Susskind, 't Hooft, and many more, said impossible. They argued for decades. That is how seriously we take information conservation. Today, many physicists believe the information does escape, encoded in subtle correlations in the Hawking radiation, scrambled beyond practical recovery, but present in principle. The black hole does not destroy information, it disperses it. The universe balances its books, always. So let us return to something concrete. That spilled coffee, or a letter you burned, watched it curl to ash and smoke. Gone? Consider what happened at the atomic level. The paper was cellulose, carbon, hydrogen, oxygen chains. The ink was pigment molecules. When you lit the match, you added energy. Molecules vibrated violently. Bonds broke. Paper molecules fragmented and recombined with oxygen, forming carbon dioxide, water vapor, and other combustion products. But every single atom that was in that letter still exists. Not one was annihilated. They merely rearranged, scattered into air, settled into ash, dispersed into the environment. Photons also carried energy and information away. And the pattern of that scattering was not arbitrary. It was determined by physics, by precise initial conditions: temperature, air currents, exact molecular positions, and the light and heat that radiated outward. In principle, if you could track every atom and photon, measure exactly where each went, account for every air molecule's vibration, you could reconstruct the letter. Not just that it existed, but every word, every loop of handwriting, the exact ink shade, everything. Can you actually do this reconstruction? Of course not. You would need impossible precision, non-existent computers. But the laws do not forbid it. The information has not been destroyed. It has been scrambled, spread out, diffused, hidden in correlations, but not erased. An analogy: a glass of clear water. You place one drop of blue ink in the center. At first, distinct. Then it diffuses. Soon the entire glass is uniformly pale blue. The drop has vanished. No, the ink molecules are still there, merely spread out, mixed. If you could tag each molecule, you would find every one. Now the remarkable thing. In ideal physics, if you could reverse every molecule's velocity at that exact instant, the ink would undiffuse. It would collect back into a drop. The movie would run backward. Perfectly legal. We never see this because the probability is astronomically small. To reverse all those velocities requires one specific arrangement out of unimaginable possibilities. The laws do not forbid it. It is merely unbelievably unlikely. But unlikely is not impossible. That distinction matters. If laws are symmetric, if information is not destroyed, why does time seem to flow in one direction? Why do eggs break but never unbreak? The answer? Entropy. Imagine a box divided in half. One side has gas, the other is vacuum. Remove the partition. What happens? Gas expands to fill the whole box. Why? Boltzmann's insight. Think from the molecule's perspective. Each bounces around following Newton's laws. It does not know about expanding. It just moves. There are many ways molecules could be arranged. All in the left half, all in the right. Spread evenly. Arranged to spell your name. Each specific arrangement is a microstate. Crucial point. Many different microstates can look the same macroscopically. If gas is spread evenly, there are countless arrangements that all look like evenly spread gas. But all gas in one half? Far fewer ways. Astronomically fewer. For 100 molecules, the most probable split is 50-50. There are about 10 to the 29th ways to choose which 50 are on the left and which 50 are on the right. But only one way to have all 100 in the left half. 1 versus 10 to the 29th. Now imagine not 100 molecules, but 10 to the 23rd, a breath of air. The ratio becomes incomprehensible. Entropy measures this. High entropy, many microstates correspond to the same macrostate. Low entropy, few. When you remove the partition, molecules bounce around exploring microstates. Because vastly more microstates correspond to spread out, the gas almost certainly ends up spread out. Not because a force pushes it, simply because there are more ways to be spread out, like shuffling cards. Start perfectly sorted. Shuffle, chaos. Why? Shuffling is random, but vastly more messy arrangements than sorted ones exist, so you get a mess. Shuffle 1 billion times, and you will never accidentally return to perfect order. It could happen, but you would need to shuffle longer than the age of the universe. This is the second law. Entropy tends to increase in isolated systems. Not because the microscopic laws force it, but because high entropy states are overwhelmingly more probable. This is why eggs break but never unbreak. A broken egg has higher entropy. Vastly more ways to arrange molecules into broken egg than whole egg. But notice, the laws have not changed. Time symmetry remains. Information is still conserved in principle. The reason for time's arrow is not in the laws themselves. It is in initial conditions. The early universe appears to have begun in an extraordinarily low entropy state, especially in how smooth and unclumped it was gravitationally. Why? We do not know. One of our deepest mysteries. But ever since, entropy has been increasing, things spreading, mixing, diffusing. moving from order toward disorder. And that is why time seems to flow, why past feels fixed and future feels open. The past is not gone. The information is still here, mixed with everything, diffused, scrambled, hidden in correlations, encoded in the universe's state. All there. We simply cannot easily read it. Now, my own contribution. Before my work, people imagined time as a river flowing steadily, the same for everyone. Newton envisioned a universal clock. I shattered that. The key, light speed, is the same for everyone, regardless of motion. No matter how fast you move, you measure light at 299,792,458 meters per second. Always. This seems impossible. If I am on a train moving at half the speed of light and shine a flashlight forward, shouldn't light travel at 1.5 times light speed relative to the ground? No. Exactly light speed relative to the ground. And exactly light speed relative to me. Both. For this to work, something must give. What gives is time. Time runs at different rates for observers moving relative to each other. Not merely appears to, time itself is measured differently. This leads to something profound. There is no universal now. What is happening right now on a distant star depends on how you are moving. If you sit still on Earth, right now on that star is one moment. If I fly past at high speed, my right now on that star is a different moment. Neither of us is wrong. There is no single objective fact about what is happening now at distant locations. In spacetime, events are points. Your birth is one point, your death another. The dinosaur's extinction, another point. One natural way to interpret this geometry is called the block universe. Past, present, and future as regions of spacetime like different places on a map. In that view, the past is not gone because the past is not really past in any absolute sense. The year 1900 is a region of spacetime. The year 2000 is another. Both part of the same spacetime. Saying the past is gone is like saying New York does not exist when you are in Los Angeles. It exists, you are simply not there. I know this feels strange. It feels like the present is special. But feelings are not physics. Physics says there is no universal privileged now. Moments are defined relative to observers and paths through spacetime. The past is real in the same way distant places are real. Let me show how this comes together. Imagine a point in spacetime, you, right now. From that point, light can travel outward in all directions. After 1 second, it forms a sphere with a radius of 299,792 kilometers. After 1 year, a sphere with a radius of 1 light year. Draw this on a space-time diagram. Time vertical, space horizontal. You get a cone. Your future light cone. It contains all events you could possibly influence. Draw the cone backward. Your past light cone. It contains all events that could possibly have influenced you. Everything that could have sent a signal reaching you by now. Your past light cone stretches back about 13.8 billion years to the early universe. It contains every star whose light has reached Earth. All that information is streaming into you right now. You are being bombarded by the past at this instant. Consider, suppose aliens about 66 million light years away have a telescope powerful enough to see Earth's surface. What would they observe today? Earth about 66 million years ago. Dinosaurs. The asteroid nearing impact. They would watch the end of the Cretaceous in real time. To them, it would be the present. But we know what happens next. It already happened for us. The light from those events is out there, spreading. Someone could watch the dinosaurs die right now if they were positioned to catch that light. And the reverse. Light from Earth right now is streaming outward. Some distant civilization might point a telescope at our location and see us. See this moment. To them, this instant would be ancient history. Everything is connected through light. Every event sends messengers in all directions. Those messengers keep traveling. The information does not simply disappear. So, why is the past not gone? First, light from past events is still traveling and reaching us. When you look at stars, you literally see ancient history. You receive mail from the past every second. Second, many fundamental laws are time symmetric. They work equally well forward and backward at the microscopic level. Third, in quantum theory, the fundamental evolution of isolated systems is unitary. Information is not destroyed, it is transformed and redistributed. Fourth, in space-time, there is no universal now. One natural interpretation is that all moments are part of one geometric structure. The past is a region of space-time. It exists. We are simply not there. Fifth, time's arrow comes from entropy, from the universe beginning in a special low entropy state, not from the fundamental laws, but from initial conditions. What does this mean? The universe is more interconnected than it appears. The present is saturated with traces of the past. Every atom carries information about its journey. Every photon is a message from history. The past is not gone. It is merely hard to read. Some find this comforting. Every moment of your life is still there in space-time. Your childhood, your first love, your achievements, your regrets, not erased. Some find it unsettling. If the future is as real as the past in a block universe picture, what does that mean for free will, for choice? I do not know. That is philosophy, not physics. I can tell you what the equations say. What you do with it is your concern. But I will tell you what it means to me. When you look at the stars tonight, you are not seeing points of light. You are seeing a kind of time machine. You are receiving messages from epochs long past. You are connected to a history stretching to the beginning of time. And somewhere, light from this very moment is streaming outward, carrying information about you to be received by unknown observers millions of years hence. The past is not gone. It is merely getting farther away. And the present, this moment, is becoming someone else's past as we speak. So treasure it, because in a deep sense, this moment will exist forever. Now let me give you one final image. Imagine a being outside time, able to see all of space-time at once. A god looking down at a map. But the map is the entire universe's history from beginning to end. What would it see when it look at you? Not a person sitting in a chair. A long, winding thread through space-time, a world line, starting at your birth, winding through all the places and moments of your existence, ending at your death. Your first step, your first word, your first kiss, your last breath, all visible at once, different parts of the same thread. To that being, your past self would not be gone. It would simply be at a different point on your world line, like a city in another country, real, existing, just not where you are now. Your past is not behind you. It is beside you in another direction, the direction we call earlier in time. We cannot be that being. We are embedded in space-time, crawling along our world lines, experiencing one moment at a time. But physics gives us a glimpse of that larger view. It shows us the universe is bigger than our experience, that time is stranger than it feels, that past and future are more real than they seem. If it is clear tonight, go outside, look up, find a star. Think about the light you are seeing, light that departed years, centuries, millennia ago. Think about the information it carries. Then think about this. Light from Earth, from this very night, is streaming outward too. Somewhere, sometime, someone might catch it, might see this moment, might wonder who was here looking up. We are connected across time, and the universe never forgets. So I leave you with one question. What moment from your past would you want the cosmos to remember forever?